You're welcome.
Yeah, so thank you very much. It's a great pleasure to be here. Aldis was my very first collaborator. And it's very easy for me to keep track on how long time we are collaborating because my son was newborn at that time. And Aldis and my son had a race who could learn Swedish first. Aldis had a small head for the first months, but then actually my son has surpassed him in this. And he's 33 years old now. So it's always a great pleasure to come here to Riga. And I will talk about my main research topic, which is negative ions, fragile quantum systems. And basically to explain why I think we should study negative ions. I mean, the main reason is that they have unique properties. It's quantum system with very loosely bound electrons. So the electron correlation is very, very pronounced. That makes test of electron correlation, which is a huge challenge in atomic theory, very suitable. But then also many applications. There are negative ions in plasmas and in astrophysics. They're used or plans to use them for cooling antiprotons. They use for heating on thermonuclear reactors, ITER, and they're very important in accelerated mass spectrometry, the carbon-14 dating technique. And I will not go into much details, but I mean, if you think about an atomic system, with you have the ground state, excited state, and the Rydberg series. Typically for a negative ion, you have much smaller, what's called the electron affinity. And you typically have one or maybe one excited state, no Rydberg series. And almost all the states here have the same parity as the ground state. So there is no fingerprint, you cannot make an atomic transition. This makes them unique, but also a little bit more difficult to investigate because there's no, you cannot do the traditional spectroscopy, there's no resonance lines to investigate. So you can only do the photonization, which we then call photodetachment. And I will just pick 3 experiments. Recent things were done on this. And the first experiment on this is a study on an element called astatine. If you don't know it, it's situated down here. It's the heaviest halogen. And it has some very special properties. It's the least abundant element on Earth. The estimated amount is 70 milligram in the crust of the Earth, integrated. It decays through an alpha decay, and basically no physical chemistry properties that are known, but it is used in something called targeted alpha therapy. You basically put an astatine isotope on an antibody injected in the body, and that is kind of diffusing in the body to find the metastasis, and then if it decays, it can kill the cell, the cancer cell. And the reason why it's so good is because the energy is good. It's like the range in the body is half of one cell length, and the daughter are non-toxic and non-radioactive. So it's just a clean system. But it's used, but it's since the properties are unknown, it's of great interest to get basic knowledge about its properties. And now, if you guys look on the theory, when we started this experiment some years ago, this is the affinities of the halogens, well established and well known, iodine, and that is a range of 1 eV in how well it was known. So basically no real value. So our aim was to make a precise measurement of this to kind of guide theory. The problem is that astatine is radioactive. It doesn't, I mean, the amount in nature is so small, so you cannot mine it and refine it and study. So we instead produce it at CERN. It's a facility called Isolde. So the basic idea is that you take the proton beam, if it doesn't go into the big ring, you can take the proton beam and shoot into uranium. And if a GeV beam shoots into uranium, you just smash the nuclei. It's not a chain reaction, but it has a brute force. And you basically produce all isotope in the nuclear chart that exists. And you can do this online. So you have basically the diffuse into an ion source, accelerate them, run them to experiment. So any isotope that lives for more than milliseconds can be studied. So we did this, and then this is the Isolde hole where now the beam of the radioactive isotopes goes out to different experiments. And to do this study, we built a detector that we call Gandalf. So the basic idea is the following: you take the ion beam, you bend it, and you bend it into a Faraday cup. You know, you have some ions. Then you put the laser beam in, and we want to measure their affinity, the binding energy. You just scan the photon energy up until you start to break them up. And if you break them up, you don't bend the astatine minus in here, but instead they progress into this plate. And this is a unique detector that we have developed, because here comes the neutral and it smashes in and it goes into a graphene coated quartz plate. Here you knock out electrons, and those electrons are then bent and counted with a channeltron. The challenge here is that the average number of atoms in this region that we got was 0.01. So most times it was empty. The number of photons in one part was of the order of 10 to the 40, and those photons passes the detector. But with timing and with the choice of the material, we managed to do this, and this is actually the kind of detector set construction. And with this short talk here, I mean, this is basically what we got. We had a standard dye laser. We scanned the laser, and we increased the photon energy until we saw it would break up. So on this scale, you have the number of astatine atoms produced by the photon. And this curve here is described by what's called the Wigner law. So, and it's only one parameter, L, and that's the angular momentum of the outgoing electron. And if you start with a p electron, it's the s electron that goes out. So you get then a square root threshold. It's very sharp onset. And with that, we could then fit this, and we got this value. This value of the affinity. And we worked together with Anastasia Bolshevsky from Groningen, and she made this calculation. And we were very afraid to interfere with the process. So actually, those two numbers were presented back to back in a conference, and we had not talked with the theoreticians when those two values were presented. And to finish this story, if we got the affinity, the ionization potential is known, and then you can calculate the electronegativity, which is kind of the key number in chemistry. Because if you compare electronegativities, you know two elements. You can basically predict what kind of bonding, if it's a covalent bond or ion bond, etc. So that was my first experiment, and now we can see here the periodic table of the affinities. We now have added this point to this scheme. Second experiment is the experiment Henning didn't talk about, and this is when we wanted to study make a precision measurement on oxygen miners. And this is the most precise previous experiment. And oxygen has two bound states in a negative ion. And if you want to measure the affinity, you should go from here to here. But with this photon energy, you can already photo detach the excited states. That means that here you have a background. So you want to determine the position of this little increase, this threshold. And if you zoom in, you see this here. And they did this very nicely and predicted this. But as you can see here now, you have like you go from 100 to 110, the signal. So you have 1 to 10 signal to background ratio. And here we decided to make use of the unique properties at Desiree, because in Desiree we can store ions for minutes or up to an hour. So that was already talked about. So what we did here, we injected O- in the ring. We applied a photon such that we photo detached the excited state, but not the ground state. And that we did for about 30 seconds. Then we completely depleted this state. When we depleted that state, we jumped the laser to the point, according to here, that we actually reach the threshold and scan over the threshold. And then you can see here, now we scan the laser, we go up on the threshold. And then in one injection, we made them 4 scans of the thresholds. And by now accumulating this, and then of course, here we have an ion beam with high velocity. So we have a huge Doppler shift. But there's an effect that is called the Doppler compression. So actually the spread of the velocity goes down if you accelerate, but you get two very shifted values. But if you basically if you measure them with parallel and anti-parallel and take the geometrical mean of those, you get the affinity to all orders. So you eliminate the relativistic Doppler shift. So here you can see the threshold in the parallel and here in the anti-parallel direction. And then we repeated this many, many times. And then we basically came up with the affinity. And this is the new value of our affinity. This was the one I showed you. We got a huge improvement in accuracy here. And this is the final value, which is now the most precise affinity measured in any system. it's so good, so we actually can measure the isotope shift. So that is what we have done, and that's another story. We just about analyzing and writing up this, so the results of that will come later. Okay, next thing, third thing I want to present, that is a technique. So now I've presented, we have a negative ion, a photon in, and knock out the electron and measure the fast neutral that is easy to detect. But of course, you can detect the electron that goes out. And assume now that you shoot in and have a p electron, so you knock out an s wave, you will get a spherical wave that expands. Now is the technique called velocity mapping, where you basically take an electric field and you smash that wave into a detector. And that's a detector is just simply a number of electric field. And then we just wanted to show this detecting scheme by taking silver and applying a femtosecond laser, so we make multiphoton about threshold ionization. And this is what we see then. So basically you see those, so this is corresponding to just coming above the threshold. Here it has absorbed one more photon that is needed, then you get higher energy. So this image is just what you see here. So basically go out from the radius, that is the energy, and the polarization is along this axis. And this, then you can do an inversion and then basically recalculate what you would have gone if you, since you have gone from a three-dimensional real wave function and put it on a projected that in 2Ds. The thing I wanted to spend a little bit of time on here is that one of my students, Michael Eklund, he has an undergraduate in mathematics, and he did this experiment that I showed you. And then he said, why not do tomography? Because we have here, and this is kind of the picture we get. And of course, we have our laser polarization. And we do this with one, and then we calculate back with the Abel inversion what you would have got. But if you now repeat this and then basically rotate this polarization, you measure this in all angles. It's like in the body scan in the hospital. And there's very well established mathematical routines to do that backwards work. So we did this. So here you can see basically what you see here of a certain case. This is silver minus, and we only go up about with 1 and then 2 photons a little bit. So this is basically a picture of the wave function or projection of the wave function. But now, of course, we can now take for area. Now I will show you a movie when we do this and make steps of 3 degrees. So now we basically make the rotation here. So now you see this, and if you now feed this movie into the tomographic mathematical routine, we can then come to this result, that we actually get a real 3-dimensional image of the system. And of course, this can also now be, you can rotate this and see. So this is basically the system we have. And I think it's a beautiful way, more kind of maybe a demonstration of the real wave functions, how this electron wave goes out. And with that, I'll just pick my final example of what we're doing. And that's actually what we're doing right now. And that is, we have studied the electron affinity of cesium. And I showed you this before, the Wigner law stating that the cross-section increases as this. And I said, it's the L here is the wave, the angular momentum of the outgoing electron. So if you take a p electron, the right part of the periodic table, you get this sharp onset where you can determine the position very accurately. But for all the other elements, the one with an s valence electron, then you get a p wave going out, and this becomes 3/2, and you get this very slow onset, which is then becomes very difficult to determine, because now the signal goes just asymptotically to 0 where you want to measure. So if you want to say where is the point where this crossing can start to increase. So then we have developed a technique where we basically, so this is now in cesium, and what you saw before was going from here to here and see the onset of breaking up. But if we apply a photon beam that is higher, so we actually go up to a 6p state, then you excite one electron goes to p state, and then the outgoing electron will be an S wave. And then we do resonance ionization going from here to here, and then we field ionize. So basically what we do is that we take our ion beam, as before with the astatine, put now 2 laser beams, and if you in this region have first photon attached and then excited, you have a Rydberg atom coming in here. Then we have an electric field looking like this. And we then set the slope of this field to be smaller, so you don't field ionize the state that you're going to. That means that the neutral coming in here will then go down, but here the field increases and is ionized in this point, which is roughly 1,000 volts, which means that now the ion has to go uphill and loses 1,000 volts, 1,000 EV in energy. Whereas the background we have here, that is collisional background when an ion collides with gas and produces a positive ion. But if you have a positive ion produced here, already here, it will be accelerated, decelerated, and come out with the same energy. Which basically means that here, now we have a position sensitive detector. So this is the square where we see the signal we have, and in this square, we see the background. So then we can discriminate background, and we can get a sharp onset of this threshold. And that's what you see here. So now we scan, and this is a far more zoomed in region. And basically this slope, you don't see now the 1/s curve here, the square root, because now we see the bandwidth of the laser and also the velocity spread of the ions. But then we make the convolution of that, and then can determine the affinity with very high resolution. And this is actually our new value compared with, and this was the value that I showed you on the previous slide. So this is, oh, sorry. This is our new value, and this is actually our most recent. We're now struggling with the referees on this paper, and he's arguing if we actually can have this high resolution. But I think we're pretty convinced that we can, that is the correct value. So this was a very quick, very fast talking overview of what you do. And then I just finish by saying that, so I just show you here that the affinity measurement and oxygen measurement has both been published in Nature Communications. The silver work was with Michael, and I here show you all the people that has been involved in those papers. So it's a lot of work. So there is a long list for the acknowledgement. Here are the PhD students that has basically the main contributors. And we have Miranda here that will present her work on producing negative ions using charge exchange in the talk after me. And I think it's very nice. I think here, being a physicist, if you look on the gender balance here, when I started in the group, there was only male PhD student in my group, but now we basically have a 50-50 distribution. And these are the agencies that have funded the work. And with that, I thank you for your attention. And if you don't, that is actually what it's saying here. Yeah.